These are your notes for Unit 4, Day 3 of Calculus. If you would like to see the warm-up, review question, or any homework questions we covered in class today, just look at your finished notes. So today we're going to keep talking about integration, and today we're going to learn how to evaluate integrals algebraically or by hand. So not looking at their graphs and finding the area under the curve. We're going to learn how to find antiderivatives, which are the inverse of derivatives, by hand. So we're going to learn some rules in order to find antiderivatives or how to take the integral. And we're going to use the properties of indefinite integrals to do this. So an indefinite integral graphically. So these are different than definite integrals. So remember, definite integrals are where you start and end and you're finding an exact area. So if we have a definite integral, remember they look like we're going to integrate from a to b f of x dx. So graphically, a definite integral, we're finding the exact area between the curve and the x-axis between a and b. Well, what happens with an indefinite integral? It means that we're not going to have any restrictions. So we're not going to start or end anywhere particular on our graph. So if our graph goes on forever, then the area will also go on forever. It'll keep going on forever in both directions. So an indefinite integral doesn't have a start or an end to its area. So that's the difference between an indefinite integral versus a definite integral. A definite integral will have a starting x value and an ending x value, and an indefinite integral won't have any of those on the integrand side. So how do we find integrals? Well, we find the antiderivative of each term, and antiderivatives are the inverse of derivatives. So what we need to do is we need to undo the derivative of the inside part of the integral. Just some things to keep in mind when we're doing this is the integral of 1 dx is often written as just the integral of dx. So if you have the integral of dx with nothing in front of it, you can write it with 1. So it's just like x is the same as 1x. And if you have the integral of 1 over x squared dx, it's often written with that dx as part of the numerator, but just remember you could separate it back out as 1 over x squared dx. Okay, so how do we do antiderivatives? Well, let's just start with the function. Let's say we want to find the antiderivative of 2x. So we want to find the integral of 2x dx. So basically, we're saying that the derivative of some function was 2x, right? So this inside piece was the derivative of some function, and we want to know whose derivative did we take to get 2x. So we need to undo the power rule. So remember when we do the power rule for derivatives, first step is you multiply by the exponent. And then step 2 is you subtract 1 from the exponent. So that's how you do the power rule for derivatives. You multiply by the exponent, and then you have to subtract 1 from the exponent. So now we want to undo these steps. So to undo those steps, you do the reverse order. So to undo the power rule, step 1 is we need to undo subtracting 1 from the exponent. So step 1 is we're going to add 1 to the exponent. So the very first thing that we're going to do if we want to undo the power rule, like the antiderivative of 2x, we first have to add 1 to the exponent, and then step 2, we have to undo multiplying by the exponent. So to undo multiplying by the exponent, we're going to divide by the new exponent. So to undo power rule, we have to do the steps of power rule in reverse, and we have to do the inverse of each of those steps. So instead of subtracting 1 from the exponent, we're going to add 1 to the exponent first. And then instead of multiplying by the exponent, we're going to divide by that new exponent second. So let's look at this. We have the integral of 2x dx. So to find the antiderivative of that, we're going to take 2x. We're going to add 1 to the exponent. So the exponent is 1 right now. So we're going to add 1 to the exponent, and then we're going to divide by the new exponent. Well, the new exponent was 1 plus 1, so we're going to divide by that new exponent. We're going to divide by 2. And so now if I simplify that, 2 divided by 2 is 1, and x to the 1 plus 1 is x squared. So the antiderivative of 2x is x squared. And you can always check your work by taking the derivative. What's the derivative of x squared? Well, the derivative of x squared is 2x. Now for antiderivatives, especially if we're talking about indefinite integrals, we need to be careful because x squared isn't going to be my final answer. I have to add a constant c, or I have to add a c to represent any constant that could have existed. So now, notice, if we take the integral of little f of x dx, we get big F of x plus c. And so now, if that c represents any constant, what happens if you take the derivative of any constant? The derivative of any constant is 0, so it goes away. So to represent any constant that could have existed on the original function, you have to add a c when you do the indefinite integral. Because when you take the derivative of this function, so this represents big F of x, so big F of x would be x squared plus c. If you took the derivative of this, so f prime of x, which we'll call little x, you would just get 2x. And that was that original function that we were trying to find the antiderivative of. So a couple ways of writing these. If you integrate little f of x dx, you get big F of x. So the antiderivative of little f of x is big F of x. Or you can write it as, if you find the antiderivative of f prime of x dx, you get f of x plus c. So these are two different ways that books and math people will show taking the antiderivative of f of x or the antiderivative of f prime of x. All right, so let's do a couple more of these. So again, to find an antiderivative, you need to undo the derivatives that were inside the integrand. So let's look at this first one. We want to find the antiderivative of x to the third minus x squared dx. So remember, the steps are you add 1 to the exponent and then divide by the new exponent. So the antiderivative of x to the third will be x to the third plus 1 all over 4. And then let's find the antiderivative of minus x squared. So it'll be minus x to the 2 plus 1 divided by 3. And then remember, to represent any constant that could have existed, we need to add c. So when I simplify this, I get x to the 4 over 4 minus x to the third over 3 plus c. And you can leave it like that, or if you like to write it so it looks more like fractions, you can. So it'll be 1/4 x to the 4th, minus 1/3 x to the 3rd plus c. And so both of those are correct ways to write that antiderivative. So remember to undo power rule, add 1 to the exponent, and then divide by the new exponent. All right, let's look at the next one. So we want to find the antiderivative, and then, well, let's just try this one. So that 3, remember the properties of integrals, that 3, since it's just a constant or a coefficient, it can be pulled to the front. So this is the same thing as 3 times the antiderivative of x to the negative 1 dx. Okay, so this is going to be 3 times, well, if this was power rule, we would add 1 to the exponent and then divide by the new exponent. Uh-oh, power rule doesn't work here. So what happens? So that means that this was somebody else's derivative. So I'm going to pull that 3 out to the front, and now I'm going to rewrite it as this, 1 over x dx. Whose derivative is 1 over x? So if I have the derivative is 1 over x, who was f of x? Who did f of x have to be if the derivative was 1 over x? Do you remember? It's the natural log. So if I want to undo the derivative of 1 over x, I would do the natural log of x. And to make sure that that x works, the domain works, we put it as the absolute value of x, because x can't be negative in a natural log function or any log function. So the antiderivative of 3 times 1 over x would be 3, the natural log of x plus c, or the natural log of absolute value of x plus c. So be careful You can try the power rule first, but if you end up with 0 in the denominator, that's your indicator that it was probably an ln instead of the power rule. All right. What if I have the integral, the integral of negative sine x dx? Okay, so I want to find the antiderivative of negative sine x. Whose derivative is negative sine x? Well, who do you take the derivative of to get negative sine x? You take the derivative of cosine x. So it's going to be cosine x plus c. And again, on all of these, don't forget to include that constant c. All right, let's keep going. Now we have the integral of x to the 1/7 plus x to the negative 1/3 dx. So again, this looks like a power rule. So we're going to add 1 to the exponent and then divide by the new exponent. Well, if I take 1/7 plus 1, that 1, I need a common denominator, and it's going to become 7/7. And 7/7 is 8/7. So I'm going to divide by that new exponent of 8/7. Then plus x to the negative 1/3, and then I'm going to add 1 to that. Well, if I'm going to add 1, the common denominator is 3, so it'll become 3/3. And negative 1/3 plus 3/3 would become 2/3, so I'm going to divide by that new exponent of 2/3, and then plus c. Well, if I simplify this, I get x to the 8/7, and remember, when you divide by a fraction, you're actually multiplying by the reciprocal, so I'm going to multiply by 7/8, and then plus x to the negative 1/3 plus 3/3 would be x to the 2/3. And then if I'm dividing by 2/3, I'm actually multiplying by the reciprocal. So I'm multiplying by 3/2 and then plus c. So the antiderivative, or the indefinite integral, x to the 1/7 plus x to the negative 1/3 dx, becomes 7/8 x to the 8/7 plus 3/2 x to the 2/3 plus c. All right. Now the next one isn't a power rule. If you wanted to, you could bring it up to the numerator by doing x squared plus 1 to the negative 1 dx. You can't just bring up each term one at a time. The whole term would have to come up together. So this is not power rule either. So that means that somebody's derivative was 1 over x squared plus 1. Whose derivative is 1 over x squared plus 1? Well, maybe you remember it is arc or inverse tangent. That's the derivative of arc or inverse tangent. So you can write arc tangent x plus c or inverse tangent x plus c. So remembering everybody's derivative, the trig functions, the e functions, the ln functions, the arc trig derivatives, make sure you remember all of those different derivatives that we learned last semester. All right, on the next one, that 2 is just a coefficient, so it can be pulled to the front. So this is the same thing as 2 times the integral of 1 over 1, the square root of 1 minus x squared dx. Well, whose derivative is 1 over the square root of 1 minus x squared? That is going to be arc sine. So this is going to be 2 times the arc sine of x plus c, or 2 times the inverse sine of x plus c. So again, knowing all of those different derivatives will come in handy for this part of the unit. All right, let's look at these. Find the antiderivative of 3x to the 1/2 plus 2x to the 2/3 plus 4x to the negative 2 plus 3x to the negative 1/2. All right, so we're going to add 1 to each of those exponents. So it'll be 3x. If I add 1 to 1/2, I'm going to add 2 over 2. So that's going to become 3 over 2. And then I'm going to divide by 3 over 2. And then plus 2x to the, if I add 1 to 2/3, I would get 5/3. And then I would divide by 5/3. So add 1 to the exponent and then divide by the new exponent. And then 4x to the, add 1 to that exponent, negative 1, and then divide by the new exponent, negative 1. Now notice the original exponent wasn't negative 1, so we're good. And then plus 3x to the, add 1 to negative 1/2, and you get 1/2, and then divide by the new exponent, and then add c. All right, I'm going to simplify that. I'm going to multiply each by the reciprocal of those denominators. So this would become 2x to the 3/2. So when I multiply 3 by 2/3, I get 2. And then plus 6/5 x to the 5/3. And then minus 4x to the negative 1. I'm going to leave it there. And then plus 6x to the 1/2. And then plus c. And that would be the antiderivative, or the integral, of that function. All right, on the next one, I'm going to rewrite it first. So this is going to be the integral of 6x to the 1/2 minus 5x to the 1/3 plus 2x to the 2/3 minus 3, and then dx. So if I found the antiderivative of each of these terms, again, I'm going to add 1 to each of these exponents. So plus 2 over 2, plus 3 over 3, plus 3 over 3. And then we're going to get 6x to the 3/2, then divided by 3/2. And then minus 5x to the 4/3 divided by 4/3. And then plus 2x to the 5/3 divided by 5/3. And then the antiderivative of -3 would be -3x, because if I took the derivative of -3x, I'd get -3, and then plus c. All right, so now if I simplified this, I'm going to multiply by the reciprocal of each of those denominators. So I would get 4x to the 3/2 minus 15/4 x to the 4/3 plus 6/5 x to the 5/3 minus 3x plus c. Again, don't forget that constant c at the end of each of these indefinite integrals. All right, again, on the next one, I'm going to rewrite it first. And so I'm going to get 4x to the -1 plus 5x to the -2 plus 6x to the -3 plus 7/3 x to the -1/2, and then dx. All right, if I find the antiderivative of each of these terms, I've got to be careful on that first one, because remember, if I add 1 to the exponent, I'll get 0 as an exponent. I can't divide by 0, so that's the natural log one. So this is going to be 4 times the natural log of the absolute value of x. And then after that, I can just add 1 to each of the exponents. So add 1 to the exponent and divide by the new exponent. I'll get plus 5x to the -1 over -1. And then plus 6x to the -2 over -2. And then plus 7/3 x to the 1/2 over 1/2. And then plus c. So if I simplify this, I would get 4 ln absolute value of x minus 5x to the -1 minus 3x to the -2 plus 14/3 x to the 1/2, and then plus c. And that would be the final antiderivative for that integral. All right, on ones like the following, what you're going to end up having to do is we're going to write these as 3 separate fractions, or in the one below it, 4 separate fractions first. So my denominator is a monomial, so I'm going to rewrite this to begin with. So I'm going to divide each of those terms by x. So this will be x squared over x minus 5 over x plus 2 over x dx. And then I'm going to simplify this into x minus 5 plus 2, and I'm going to write that as 2x to the -1, and then dx. And now I can find the antiderivative of that. So if you have a fraction where the denominator is a monomial, right, it's one term, then you can separate it into separate fractions and then reduce each of those fractions. So the antiderivative of this would be x squared over 2 minus 5x, and then be careful on this one because that's the ln. So this will be 2 times the natural log of the absolute value of x, and then plus c. Okay, on the next one, again, I'm going to rewrite it as separate fractions. So this is going to be the integral, or the antiderivative, of 9x to the 3rd over 3x to the 3rd plus 8x squared over 3x to the 3rd and plus 3x over 3x to the 3rd minus 4 over 3x to the 3rd dx. And now if I rewrite that by simplifying it, I would get 3 plus 8/3 x to the -1 plus x to the -2 minus 4/3 x to the -3 dx. And now I can find the antiderivative of each of those. So I would get 3x, and then be careful on this one because it's x to the -1, so it'll be plus 8/3 ln absolute value of x. So ln absolute value of x, and then plus x to the -1 over -1. and then plus 4x to the negative 2, and then plus c. So add 1 to the exponent. Sorry, I multiplied by the exponent. Be careful. So add 1 to the exponent, and then divide by the new exponent. So this would be negative 6x to the negative 2. And so if I simplify this, I'd get 3x plus 8/3 times the natural log of the absolute value of x minus x to the negative 1 minus 2/3 x to the negative 2, and then plus c. All right, let's look at some more examples. The integral of cosine x over sine squared x dx. So the hint is to rewrite the denominator using sine x times sine x. So this would be cosine x over sine x times sine x dx. And so I'm going to rewrite this as cosine x over sine x times 1 over sine x. And now I can use my reciprocal and quotient identities. Cosine x over sine x is cotangent x, and 1 over sine x is cosecant x. So that's cosecant x, that's cotangent x. So I'm going to rewrite this as cosecant x times cotangent x dx. Well, whose derivative is cosecant x cotangent x? Well, the derivative of cosecant is negative cosecant x cotangent x. So in order to get this to be positive, I need it to be negative cosecant x plus c. So if I took the derivative of negative cosecant x, I would get negative and then negative cosecant x cotangent x, which is what I wanted. So the antiderivative of cosecant x cotangent x is negative cosecant x plus c. So the derivative of cosecant is negative cosecant cotangent. And so since I want it to be positive, I need negative cosecant x plus c. So again, remembering all the trig derivatives is going to be helpful. So maybe review those. All right. Another thing that you might end up having to do is long division. So if I have x squared divided by x squared plus 1, so notice this is not a monomial. So I'm not going to split it up into two fractions. So instead, I have to use long division. So if the denominator is not a monomial, you might have to use long division in order to figure out this integral. So long division says you take the numerator divided by the denominator. So x squared times what is x squared? Well, I need a 1, and then you multiply it out. So we have a 0 here. So then I would get x squared plus 1, and then you subtract going down. So this would be negative 1. So then it's plus the remainder over what you were dividing by. So now this integral can become 1 minus 1 over x squared plus 1 dx. Well, now we can take the antiderivative of each of these. What's the antiderivative of 1? Whose derivative is 1? Well, it's x. And then whose antiderivative is 1 over 1 plus x squared? That would be arctangent. So this is going to be x minus the arctangent of x plus c. So sometimes you might need to use long division in order to simplify the inside of the integral so you can take the antiderivative. All right, so those are indefinite integrals. So the big thing is remember to add c to the end of all of them if they're indefinite integrals. And you're probably going to want to review all the different derivatives that we've taken. All right. Well, what if we want to be able to find c? So if they want us to be able to find c, so to find the exact value of c, they have to give us something called an initial condition. So they have to give us a point that works in the original function. So they're telling us, we're going to use f. So they're telling us that f at 0 is 1. So they're telling us that we have the point 0, 1 on the original function. So we're going to use that point. So x equals 0, y equals 1. We're going to use that point to find c. So the first thing we're going to do is they're telling us that the derivative is cosine x. So we want to undo the derivative. So to undo the derivative, we're going to find the antiderivative. So whose derivative is cosine x? Who did you have to take the derivative of to get cosine x? Well, you took the derivative of sine x, and then it's plus c. So we know that the original function is going to be sine x plus some constant c. Well, now in order to find c, we're going to use that initial condition. So what we're going to do is we're going to plug 1 in for the y, or the f of x, and we're going to plug 0 in for the x and see what happens. So I get 1 equals sine of 0 plus c. Well, the sine of 0 is 0, so I get 1 equals 0 plus c, so c is going to be 1. So now that we have that, we just substitute it back in, and so now my particular solution, so this is called a particular solution, because I'm finding c. So my particular solution is going to be sine x plus 1. So this is my particular solution. And then this one right here where I had the plus c, this is called the general solution. So if you're going to leave the c in, you have a general solution. And then if you're solving for c given an initial condition, that's called the particular solution. All right, your homework is the worksheet from class today. So let me know if you have any questions.